One of the two postulates of Einstein's theory of special relativity is that the speed of light in free space is invariant. Explain what is meant by this postulate. Speed of light in free space is independent of relative motion of source and observer. B. State the other postulate. Laws of physics unchanged from one inertial frame to another. Two detectors are measured to be 34 meters apart by an observer in a stationary frame of reference. A beam of pi mesons travel in a straight line at a speed of 0.95 seconds past the two detectors. Calculate the time taken in the frame of reference of the observer. It means in the stationary frame of reference on the Earth or in the laboratory for a pi meson to travel between two detectors. And we know that what time it's what distance in our reference frame. It's 34 meters divided by speed is 0.95 c. It's speed of light. It's 3 times 10 to the power of 8, and it becomes 1.2 times 10 to negative 7 seconds to two significant figures. The next. Pi mesons are unstable and decay in a half-life of 80 nanoseconds. It is found in experiments that approximately 75 of the pi mesons that pass the first detector decay before reaching the second detector show how this provides evidence to support the theory of special relativity. In your answer, compare the percentage expected by the laboratory observer with and without application of the theory of special relativity. First of all, notice that it may be not clear, but this 80 nanoseconds it's time in which pi meson is stationary, or pi meson may be stationary at all. And again, notice that 75% it's decayed, but when you consider law of decay, the number of undecayed or remaining radioactive materials initial E2 minus lambda T, something like that. So don't get confused. 25% remaining. And let's review key concepts. So there is some stationary reference frame on the Earth or relative to a laboratory, and there is moving reference frame where pi meson is at origin, and there are two detectors. And if there is, for example, a stick of 1 meter in laboratory reference frame or on the Earth, if we put this stick in moving or in the rocket, for example, and from notice that if you are in the rocket, you will measure also 1 meter because the stick will be stationary in the rocket's reference frame. But from the Earth, we will measure less value. So you will measure, for example, 0.8 meters, and it's called contracted length. And if it's L0 on the Earth, it will be L0 over gamma on the rocket, but measured from the Earth. So we will measure contracted on the Earth. We will measure contracted length of something in the rocket, and gamma it's a factor which is equal to 1 over root 1 minus v squared over c squared, and it's always greater or equal than 1. And graph looks like this. It rises up rapidly up to infinity when v tends to speed of light, v gamma. And about time, L0 is called a proper length, and by definition a proper length is in reference frame where the object is stationary, not moving. About time, proper time, its smaller value, it will be in that reference frame in which two events take place at the same point, and reference frame or pi meson, it's always at the origin of a moving reference frame. And if we consider one detector, another detector, so pi meson is always at the same position relative to moving reference frame. So moving reference frame measures proper time, proper smaller. But from the Earth, we'll watch slow motion and we'll measure dilated, it means larger time, dilated time. So this value measured in the laboratory is dilated time in the rocket or in the moving reference frame. Here it's reference frame relative to pi meson. Time will be divided, it will be 1.2 times 10 to negative 7 divided by gamma. It will be less, it will be proper time. And now let's consider what is required without special relativity formula and in laboratory frame. Let's calculate number of half lives taken during pi meson travels from one detector to another. So in the laboratory frame, number of half-lives, it becomes what? Time in laboratory, it's 1.2 times 10 to negative 7 or 120 nanoseconds divided by time of one half life, it's 18 nanoseconds, and it becomes 6.7. And the number of remaining pi mesons, it becomes 1 over 2 to the power of 6.7, just this number of remaining or activity. It's what initial 2 to the power of minus what t divided by half a life, and hence it becomes initial. But notice that it's number of remaining. Decayed, it's total number minus number of what undecayed, but it's more useful to consider remaining or undecayed. Remaining or undecayed number of pi mesons, and it becomes 0.96%, not 25, so much less, and definitely it's not consistent with the experiment. And with special relativity formula in laboratory frame, time will be the same, 120 nanoseconds, but 18 nanoseconds, it's time in pi mesons reference frame of moving. But in our stationary, we will measure dilated time, so half-life becomes 18 nanoseconds multiplied by gamma, and it becomes 58 nanoseconds. And now number of half lives becomes 120 nanoseconds divided by 58, and it becomes approximately 2, and 1 divided by 2 squared, it's 1/4, or it's 25% undecayed or remaining, which is consistent with the experiment, and hence using special relativity gives agreement with experiment. And it's enough for this question. But to be more clear, let's consider how it is consistent with the experiment relative to moving reference frame. We have considered relative to lab frame, but let's consider relative to moving reference frame. Relative to moving reference frame, in moving reference frame, we will measure contracted length. Length will be not 34, but 34 divided by gamma. But half-life, it will be 18 nanoseconds, because it is measured in moving reference frame, and time to travel between two detectors in moving reference frame, it will be what, 34 divided by gamma and divided by 0.95 C, and it will be 34 divided by speed, it's our 120 nanoseconds divided by gamma, and hence you can see that number of half-lives, it becomes 120 nanoseconds divided by this gamma and divided by 18, and you can see that 18 times gamma, you get the same this value 58, and you get 2 half-lives, which is consistent with the experiment. So it becomes number, it's 2 half-lives, so 1/2 squared, it's 25% undecayed. So it's consistent with the experiment, and that's all for this question.